Hello guys, and welcome back to our YouTube channel. In this particular lesson, we are looking at integration by substitution. Integration by substitution, and we will also touch integration by parts. Please you can watch the previous two videos which are on introduction to integration and the second one on integration of rational functions. Let us begin with this lesson. So with integration by substitution, we are going to look at the cases as follows. We have simple and direct, which is the first one, and we see what happens and why we have to apply this case. So if we have an integral, we first of all have to observe if the function is a product. If the function is a product. So if it is a product, then we check, the second thing to check is if one of the functions in that product is a derivative of the other. If the answers to these two questions are yes and yes, then we let the one that is differentiated to give the other to be u, and we proceed as follows. Let us do this by illustration with an example. So suppose we have to evaluate this integral, the integral of 2x into x squared plus 3 dx. Now we look at these two functions. This is a product. This is the first condition. It's a product. And secondly, when we differentiate x squared plus 3, it gives us 2x. So the answers are yes for the first case, it's a product, and yes for the second. When one is differentiated, it gives the other. So in this case, we apply what we call substitution. And this particular case is simple and is direct because you don't have to do any adjustments like you saw in rational functions. So we let our u to be equal to this one, that when we differentiate we have the other. So let our u be equal to x squared plus 3. Then what will be du? Du, differentiating both sides with respect to their variables, will give us du to be equal to 2x dx. Now I can now do this integral as follows, or evaluate it as follows. This integral now becomes the integral of, if you look here, we have 2x dx, and from this my letting on the right hand side, this 2x dx, I can replace it with du. So I've replaced 2x dx by what? By du, which is what I have on the right hand side. I equally said let x squared plus 3 be equal to u, as you can see here. So I'm going to also replace this x squared plus 3 by u. So you can see there is some sort of transformation, okay? Transformation of the variable. I can now integrate this function with respect to u, and this will give us u squared on 2 plus a constant of integration k. This is what we have. But this function was originally given in terms of x and not in terms of u. So I have to replace these variables by the signs, and this will now give us x squared plus 3 all squared, all that on 2, plus I have to modify this my constant a bit, so I will now call it k prime. Yeah, it's still a constant, call it k prime. So this case is actually simple and direct case. Let's look at more examples on this. Alright, example 2. So with example 2, we have the function 10x into 5x squared minus 1 dx. So we have 10x into 5x squared minus 1 dx. So if I look at this function, I look at the conditions. If I differentiate 5x squared minus 1, that will give me 10x. So this is also a simple and direct case. So what do we say? We say let u be equal to 5x squared minus 1. Then we differentiate both sides with respect to the variables. We will have our du to be equal to 10x dx. That will give us 10x dx. So back to our equation, we can now replace this 10x dx here by du. So we can replace all of this by du. So this becomes du. And we replace 5x squared minus 1 by u. Remember what we said there, that let 5x squared minus 1 be equal to u. So we now have to integrate with respect to du. So this will give us u squared as well on 2 plus a constant of integration. And we now replace these by the original variables that were given in the equation, and this will actually give us a value of so that is what we have. That actually gives us a value of 5x squared minus 1 all squared on 2 plus a constant of integration. Okay, let us now look at another example. So example 3, we have 4x into 2x squared minus 5 all raised to the power 3 dx. So what do we do with this particular case? In this particular case, let us look at this function very well. Here, it will not make sense to say, let 2x squared minus 5 to the power 3 be equal to u. Because when we differentiate that, we are never going to have 4x. So in this case, what we are going to do is we use just the core. We use the core of the second function. That is, we'll let u to be equal to 2x squared minus 5. Because we know when we differentiate 2x squared minus 5, it's going to give us 4x, and that is what we have here. So our du now will become 4x dx, which we can now do replacements here. 4x dx can be replaced by du, and we know that 2x squared minus 5 is equal to u. We now replace it by that value as well. So integrating this will give us u to the power 4 on 4 plus a constant of integration, and we replace these variables by what was given in the equation. So we will now be left with 2x squared minus 5, all of that squared on 2 plus a constant of integration. Example 4. So with example 4, we have minus 3x squared into 1 minus x cubed all raised to the power 7 dx. Alright, so we look at this question as well. We start if we differentiate the core of the 1 minus x to the power 3 all raised to the power 7, that gives us minus 3x squared. So we'll start by letting 1 minus x to the power 3 to be equal to a u. We differentiate both sides, we'll have the u to be equal to minus 3x squared, and we replace this in our function here. So minus 3x squared dx we replace by du, and 1 minus x cubed will replace it by u and raise it to the power 7. All of that raised to the power 7. So integrating this now gives us u to the power 8 on 8 plus a constant of integration, after which replacing the values we are left with 1 minus x to the power 3 all raised to the power 8, all that on 8 plus k prime. So we have seen the cases where we can integrate simply and directly. Now, what happens if differentiating one of the functions gives us a value that is not equal to the other function that we have in the product? Let's see what happens in case 2, which is simple now with adjustments. The adjustments here is a numerical adjustment like we saw in rational functions in the second lesson. So if the function is a product, that's the first thing, is a product, and then secondly we check if one is the derivative of the other times a given constant. So when we differentiate one, we have the derivative of the other, or we have a derivative which is equal to the other function times a given constant. So this is how we proceed with this one, just like adjustments we saw in rational functions. For example, here we have, when we differentiate x squared plus 3, that gives us 2x. But this function that we have here is not equal to 2x. Normally, in this case, we can rewrite it as a product of 4 and 2, such that we'll have 4 outside this sign. And we'll have this directly, and we apply the rules of integration. We can still do that, or we might decide to do some adjustments. So our u here is x squared plus 3. Our du is 2x dx. And here, I'd like to do it directly. So our 8x dx is not equal to what we have here. So we start, our du is 2x dx, but what we have in the derivative here is 8x dx. So what do? We have to do some adjustments. We see that if we multiply 8x dx by 4, we have 2x dx. So let's see how we adjust this. We are going to replace the 8x dx by 4 times 2x dx. So that's what we are going to do here. So instead of writing 8x dx, we replace it by 4 times 2x dx as follows. So our du will now be equal to, so from here now, since du is equal to 2x dx, I want to make this one to be 8x dx. So I can replace my 8x dx by 4u du. But this is a longer procedure. This is it. So we have 4u du. And when we integrate this is what we are going to have. We will see a shorter way to do it in the second example, and I think that will be pretty cool. Yeah. Please, if you have your questions, because this broadcast is live, you can leave them down, or you can visit www.gcemathspanel.blogspot.com, where you have all of this information. And please don't forget to subscribe to this channel for more updates. So let's take another case again, simple with adjustments, which is number 6. So we have the integral of x into x squared minus 1 dx. So with this, we can just do the adjustment directly. So this is what I was saying. When I differentiate this core, I have 2x. So what do? I'll place a 2 here, multiply this function by a 2, and balance it outside by a half. So this is direct balancing. Like in the previous question, it is shorter and faster to be done like this. So my integral now has no problem, because when I differentiate x squared minus 1, I have 2x. So let my u be equal to x squared minus 1. Differentiating both sides to give me du to be equal to 2x dx. And I can now come to my function and replace this 2x dx by du. So that's my du. And x squared minus 1 by u. So my integral now is a half u squared, all that on 2 plus k. That gives us u to the power 2 on 4 plus k. And we now substitute these values and adjust this variable from k to k prime. Equally, we can observe from example 7 that for this particular integral, here we have x squared minus 4, all this raised to the power a half. So we can let our u to be equal to this x squared minus 4, because if you differentiate x squared minus 4, you're going to have 2x. So we can do some balancing here, right? So we do our balancing, multiply by a half outside. So from here now, we can let our u to be equal to x squared minus 4. Let u to be equal to x squared minus 4, and du will be equal to 2x dx. I can now conveniently replace this my 2x dx here by du, and here we have u to the power a half, the integral of u now to the power a half. So applying the law of the rules for integration, this will give us u to the power a half plus 1, which is u to the power 3 on 2, all that on 3 on 2, times the half outside plus the constant of integration. So this will just give us 1 over 3 u to the power 3 on 2, all that 1 over 3 u to the power 3 on 2 plus constant of integration, and we can replace that u now by x squared minus 4 and k by k prime. Okay, next example, let us look at these questions. Okay, so you get some questions and you answer them. So that was integration by substitution. Integration by substitution. Now, at times we have a product, the product of functions, that there is no way for us to do that integration. Differentiating one does not give the other, and we have to use another method for those type of problems. That is where we find ourselves, or that is what brings us to integration by parts. Integration by parts. So this is our next lesson that we're looking at. Our next short lesson is on integration by parts. Let's take some few simple integrals. So integration by parts is the product rule for integration. It is mostly used when there is the existence of logarithmic, exponential, trigonometric, inverse trigonometric, and polynomial functions in the product. So we mostly use integration by parts when this occurs, and this is what you observe. So with the integration by parts, the formula that I usually follow is a product rule for integration. And there is a way of choosing the u. The order of choosing u, the function u, should be as follows: a logarithmic function, inverse, trig, polynomial, exponential, and trigonometric. So the formula or the mnemonic is lipet, whatever you call it. So this is the order for choosing the u. Let's take an example here. So you have this the integral of x e to the power x dx. We know that if we differentiate e to the x, you have the same e to the x, right? So it does not give us this other function as we saw in differentiation. So that is why substitution fails in these types of problems. What we have to do is integration by parts. So with integration by parts, there's an order of choosing them, the function u. So here we start by letting u to be equal to x. Yeah, because we have looked at logarithmic, there is no logarithmic here. Inverse trigonometric, there is none. Next one is polynomial. Is there a polynomial? Yes, x is a polynomial. X falls under polynomials before exponential. So our u should not be e to the x, our u should rather be x from lipet. So now our du will be equal to 1, and then this other function should be dv. So the two functions in this question should become, this one is u, while e to the power x is dv. This is good. Right, now we have to, since we have u and dv, we have to look for du and v itself. So therefore from here, du will be equal to dx, and since we have dv, we need v, so we can apply the formula. So v will just be equal to integrating both sides, okay? So v will be equal to e to the power x. Normally when you integrate, you don't consider the constants here. You don't consider the constants. Okay, so the formula for this type of integrals is given by, when you have the integral of u dv, where one function is the u and the other function is the dv, the integral becomes, as soon as you correctly choose your u, the integral becomes uv minus the integral of v du. And this rule actually comes from the derivative of product. If you look at the product rule, you see where this one comes from, because the derivative of uv is equal to v du plus u dv. In that case, if you do some sort of trying to integrate both sides now, it brings us to this. These are enough reserved for the further maths lesson. So this our integral now becomes, applying the formula x e to the power x dx, this integral now becomes our u is x, our v is e to the power x, minus the integral of v, our v is e to the power x, and our du is 1. E to the power x, and our du is 1 dx. Now we know the integral of e to the power x dx is just e to the power x. So this integral now becomes x e to the power x minus e to the power x plus the constant of integration. So this is integration by parts. This is integration by parts. Let's take another example. Let's not forget our Lippert's rule. So in example 2, we have the integral of ln x. Alright, I've not put x here, actually ln x. Integral of ln x. And if you look at ln x has a special way of integrating it, log x and all of that. Because with ln x, we consider the number, the unit 1 to be the other function. So we have two functions. So the first unit is 1, the other one is this ln x. So the order of choosing this, we have logarithmic function. Once you choose a u, according to Lippert, there is a logarithmic function here, so that one should automatically become a u. So a u is equal to ln x, and a dv is equal to 1. So from here we can look for du. A du will be equal to the derivative of ln x is 1 over x, okay? So du will be equal to 1 over x. And now that we have dv, we have to look for v. Our v will be equal to the integral of 1, which is x. So we can now apply formula. So the integral of ln x dx, like I said before, is 1 times ln x. It give us x ln x. That is u, which is ln x, and our v, which is x. We can now write ln x. So we write x ln x minus the integral of v. The integral of v, our v is x. Integral of v du. So this is v, and this is our du. Or so this x will cancel out with this one. We'll just be left with the x, the integral of the x. So this integral finally gives us x ln x minus x plus a constant of integration. Plus a constant of integration. Let's take another example. So in the next video we continue with more examples, and you have to see how you can do this one according to Lippert. Which of them should be x and which one should be u and which one should be dv? Logarithmic, there is none. Inverse trig, there is none. Polynomial, yes. So this should obviously be a u. Thank you so much for watching, and in the next lesson we will continue with integration by parts, and we'll look at exponential and logarithmic functions. Guys, please don't forget to subscribe and visit www.gcemathspanel.blogspot.com. There we have a compilation of past papers for you. We have information on concours and exams, scholarships and travels abroad, and you can talk to us directly. We have model quizzes there and mathematics notes, and most importantly we have corrections for past GCE papers. Corrections for past GCE papers which are for free, the markers guides and all of that. Don't forget to join with us, to share and to subscribe to this channel. Thank you so much, and bye bye.